Obviously, one way you can write this equation is to take this square root of beta out, and you get this. Okay. But now, there's something that can come out of this equation, which is kind of interesting, and it's a natural consequence of this equation, is that for this material, for crack to grow, basically, this sigma c has to have a critical value. I'm going to write it here, that I'm going to show with sigma c, and sigma c is square root of pi a times y has to be equal to K1C. Okay? So that tells us how much stress in the far field is required for for the crack to grow. And obviously, the larger the crack, the smaller far field stress is required. Now, one thing I didn't explain to you is this K1. So K by itself is a stress intensity factor. K over square root R gives you a measure of a stress. Kc is the critical value of the K, which is the fracture toughness. So K by itself is not a material property, but Kc is a material property. It's the highest value of K that the material can tolerate. And 1 describes the type of loading. And to understand what I mean is, there are 3 types of loadings, 3 basic types of loading, and everything else can be a combination of these 2 that we will talk about. Mode 1 fracture is when we have a crack like this, and we're trying to open it like that. Okay, it's basically opening the crack. In this case, far field loading is perpendicular to the surface of the crack. This is what we call mode 1. So everything I explained to you is mode 1 so far. And if you look at the geometries I showed you already, they were all mode 1. And so mode 1 is not necessarily just one load. It could be a distributed load. As long as they're perpendicular to the initial fracture surface, we're fine. We still call it mode 1. But everything I said earlier, you can also explain them for mode 2, for mode 3, and all that. Okay, so you can have K2, you can have K2C, you can have K3, you can have K3C. But what is K2? K2 is in plane shear. So basically, it's the loading is parallel to the fracture surface, and it's defined by this far field loading. So you're basically trying to shear off the crack and open it. Mode 3 is anti-plane. So basically, imagine this is a loading that goes through. This is the loading that comes out. So you're trying to open the crack. Like if this is the crack, the initial crack, you're opening it like that. Whereas in case 2, you were opening it like that. And in case 1, opening like that. 1, 2, 3. Okay? And so obviously the value of K1C is not the same as K2C, which is not the same as K3C, because failure and fracture growth is not only a local phenomenon. It has to do with how energy redistributes in the sample. So now, going back to the last equation that I derived for you, basically we can calculate the critical, far field stress that is required to grow the crack. Here, I'm limiting the discussion to K1, and this is the material. It's C here, which means this guy is a material property. The geometry is stored in this parameter, non-dimensional parameter, and this is the initial length of the crack. Now, the concept of fracture can also be taken into consideration by looking at energy landscape of the material. In order to understand the energy considerations, I want to start with a simple, very simple geometry. Again, we're going to limit the discussion to mode 1. So imagine this is our material, and it's being loaded in mode 1. So basically, in this case, this is from here to here is nothing but my initial crack length. Now, one thing I want to say here, and if you, I'm hoping you're comfortable with it, but if you're not, that's the time to understand it. These portions here and here are traction-free, which means no force is directly applied, no force is applied to these regions, just on the surface. So basically, if I want to be perfectly clear, and sometimes traction is defined as a stress vector. I'm not very comfortable with that terminology, but for people whose background is not mechanics, traction or stress is scalar components of a vector that we call traction. Okay, so traction is force per unit area in the case where area becomes extremely small. Okay, so basically, these regions are traction free, so are these regions. And they have to be traction free because there's nothing on this side or nothing on this side to, there's nothing here to apply any force to these guys. These are traction free. Now, let's say the crack grows by some amount that I'm going to show with a different color. So this becomes the crack. So, and so basically now I have the crack that has grown by some amount delta A, okay? Now, you remember I said these parts are traction free? No, not only these parts, but also this extra region is also traction free. Okay, so in the past, these parts were traction free, and these parts in the very vicinity of these surfaces didn't have much elastic energy. But these parts were taking a lot of the stress. So before crack growth, there was some energy stored in these parts. Now that energy is released because the crack has grown, and these parts that I'm showing with purple are now traction free as well. So energy, the elastic energy that was in them now is released. Where did that energy go? Well, that energy went into breaking the bonds between these atoms that were here. Okay? And the balance between these energies, the elastic energy that would be released if crack grows by delta A, and the energy you need to give to those atoms to break the bond between them. So the balance between the elastic energy that would be released if crack grows by delta A, and the energy that you require to break these bonds, the balance between these two energies tells you whether the crack will grow or not. Okay. Now, the consideration of these energies will allow us to have another parallel description, quantitative description of crack growth that goes with the last equation that I showed you. If I go back to these guys, so basically this schematic is just showing us the concept that I was trying to explain to you. In the vicinity of these guys, the elastic energy is released, and this energy is used to break these bonds. But how much energy do you, so the part that's about elastic energy, we can calculate it. It's complicated. We're not going to get there, but there's some more advanced courses that you can learn. But the energy that you require to advance the crack often has two components. And I show it with G1C. One, again, is for the crack mode of, mode of the crack growth, which in this case is this and that. And C is because it's basically critical value, has two components. One is the energy that you need to break right on the surface, the energy of the bonds, and there's two here because you have this crack grows by delta A, you're opening two surfaces, the top and bottom, and a plastic contribution. So basically, this is kind of a deviation from linear elastic fracture mechanics. This is an amendment to that says, well, if you want to grow the crack, your elastic energy that you release has to be able to overcome the plastic deformation, the energy dissipated by plastic deformation, plus the energy to generate new surfaces. I am going to stop here and continue in the next video.